Good morning. My name is Suksagar Dubey. I am pursuing my master in quantum technology. There is too much discussion is going on about quantum and its application. So one of its application is in machine learning, and we call it quantum machine learning. So this quantum computing speed up some subroutines of quantum computing of machine learning. So to get more insight on this, we have Dr. Abhay Shastry. He is the postdoc in Computer Science and Automation Department in ISC, and he is physicist. His doctoral work deals with theoretical question pertaining to nonequilibrium quantum system. Now his interest area is to apply the methods and tools of statistical physics to understand machine learning and deep learning. So welcome to Dr. Abhay Shastry.
No, I signed it yesterday.
Sir, floor is yours.
No, thanks. Hi all, thank you for that introduction. I've organized this talk in this way. For the first part, as he said, there's a lot of hype in the media. So we'll get some snippets on how it is covered in the media. Then I want to have a sort of tutorial for about 20 minutes, sort of set the basics of quantum computing itself before moving on to the machine learning parts. So as he said, the promise is that it can speed up certain subroutines in machine learning. So generally we work in that quantum classical hybrid setting, where some parts of the computation are done on a quantum machine and some is done in the classical machine. So yeah, we'll discuss that towards the end, where we'll also discuss some of our results pertaining to kernel methods. And if time permits, I'll talk about some exciting work that is recently being done. There have been claims of exponential advantages, for example, in the recommendation system problem, which have been backtracked. That is, they've shown that classically also you can have that kind of speed up, and so that reduced to at most a polynomial speed up in the quantum case, and it's probably much easier to implement it classically. So, all right, so let's look at how it's covered in the media. So this is the YouTube generation, right? You guys all social media, everything. So do you know this person, Michio Kaku? So yeah, he gets a lot of airtime on different podcasts, whatever, Joe Rogan show, this, that. So you can hear him say things like this. I'm quoting him almost verbatim here from one of the podcasts. A quantum computer is infinitely more powerful than a classical computer, because the state in a quantum computer can point in any of the infinitely many directions, whereas the classical state can only be up or down. So he says like up, down, quantum, infinite number of states between. So sort of, okay, there are other types of wrong publicity that happens, which is quantum computer is powerful because it can try all solutions in quantum superposition, all meaningless sentences. And so I would urge you to go read Scott Aronson's blog. He keeps a very nice blog. And a very recent post on Michio Kaku's book, Quantum Supremacy, he says, don't buy that book, right? And if you go to his blog, he first says, if you take nothing else from this blog, quantum computers won't solve hard problems instantly by just trying all solutions in parallel. That's just, yeah, you should not have such views on it. So now, you can go ahead and ask ChatGPT what it will tell you. Explain to me quantum computing in simple terms. It's actually suggested as one of the searches. So it says, okay, here sort of it says it can simultaneously be 0 and 1, thanks to a property called superposition. And yeah, so it's talking about superposition. You see this word simultaneously thrown around, right? And then, of course, it will talk about the other magical thing in quantum computing or quantum mechanics, which is entanglement. Here you see this kind of language. The state of one qubit will instantaneously affect the state of its entangled partner, even if they're far apart. So it's like this is a throwback to the old discussions, that is spooky action at a distance. And so it's not useful to phrase these things in these terms. So basically, if you read this, you'll come away with the impression that, okay, superposition and the spooky entanglement, that gives me the quantum advantage, right? Like, of course, you have to go into the details of a problem and correctly analyze things. It's this kind of language. It has zero information content, maybe even negative information content. Okay, so what you have to do to properly understand it, read the first 2 chapters of Nielsen and Chuang, and to get this is a book that you all are familiar with, I'm sure, and to get a very nice physical interpretation of things, all kinds of debates regarding wave-particle duality, complementarity, entanglement, and things like that from a very physical perspective. I'd recommend this book by Harosh and Raymond. I think it was mentioned that Harosh had visited. He won the Nobel Prize in 2013 or something. Yesterday it was mentioned that he visited. I see. Okay, so are you all familiar? So I'll try to have like a more interactive session in the first part at least. So there are no chocolates, but feel free to answer them. So are you familiar with this type of setup? What is this called? This Young's double-slit experiment, yeah. So you can send single atoms through this source, and then it's shown in experiments conducted in the 80s and 90s that single atoms, you can send them here, and then what you get after a while of observing the screen is that they form fringes, just like you have for light. So these are known as matter waves. So, so this is the Young's double-slit experiment. And this type of thought experiments were discussed in between Bohr and Einstein debates in the Solvay conference. A lot of discussions regarding wave-particle duality, complementarity, and things like that. And asking the question, what happens if we try to acquire information about which path is being taken, right? All of these debates have happened. And let me ask you, is superposition a quantum phenomenon? Is it a purely quantum phenomenon? No, right? Like classically, this is ubiquitous. You can have like ripples on a pond, sound, light, all of them can show interference. Okay, so we'll come to, so after all of those discussions in the 20s, they've come up with a view, right? Like an interpretation of quantum mechanics. That's known as the Copenhagen view. You can just put it down as a set of postulates. So I'm sure all of you know these set of postulates. And state of a quantum system is represented by a vector in the Hilbert space. Okay, it lives in a Hilbert space. Can anyone tell me what a Hilbert space is? Right. It's a vector space on the complex field with an inner product. And there's one more property. Huh? Yeah. Right. Inner product is there given. There's one more property about completeness. That so all Cauchy sequences should have limit points in the space itself, right? But that's the other property which makes it a Hilbert space. And For finite dimensional spaces, that doesn't matter. It is always guaranteed. So in quantum computing, you tend to work with finite dimensional Hilbert spaces. And all physical observables correspond to a Hermitian operator on the Hilbert space. So what kind of operators are these? These are linear operators. So it's all linear algebra written in strange notation, right? For those of you from engineering backgrounds who are not familiar with this Ket notation, I think most of you are familiar with the bracket notation, yeah. So this third postulate, this is the measurement. Measurement of an observable A yields one of its eigenvalues. So you'll always get one of those eigenvalues. And you can always do a spectral decomposition of this, where AI are a set of bases which are orthonormal, right? So that's a very old result from linear algebra. And the expected value of a measurement is given by this expression. This is just like psi transpose here and psi there. So this is a number. What kind of number is it? It's a real number. Yeah. So, and then this is the Schrodinger equation, which tells you how a state evolves. It evolves according to a unitary transformation. So all operations that you can do on a quantum computer are unitary. Unitaries are norm-preserving, right? Just to. Okay, so we'll come back to superposition. We'll take the simplest system, which is a two-level quantum system. This is known as the block sphere. I'm sure you've all seen this. You can represent any arbitrary two-level system state in this way, with two parameters theta and psi, which denote the angles here. And in quantum mechanics, these global phases don't matter. It's only the relative phases that have physical meaning. And when you do quantum computing, you assume that 0 and 1 are the eigenvectors of the poly Z operator. That's just standard way of doing things. Or rather, you define poly Z as 1 minus 1, the diagonal matrix 1 minus 1. That's okay. So Pauli operators everybody knows, right? What are the eigenvalues for the Pauli operators? Right. Okay, so I'll come back to that third postulate. Among all of the postulates, only one of them introduces randomness or stochasticity into your system, which is that it's the measurement, right? Because otherwise everything is deterministic here. Okay. So now measurement of an observable M, if you have a state described, any state can be described in the basis of that measurement operator. And that's what I wanted to make this point, that state vector is not to be thought of as a random variable. It evolves completely deterministically. Only the measurement process brings about some randomness. That is, the probability of measuring this particular eigenvalue is given by that. Do people know what this rho is? It's just a different notation of writing the same thing. It's the density matrix. All are aware of that. Okay. Okay, so you can look at the expectation value of M. You can calculate its variance according to these probabilities. Okay, so when you have multiple particles in the system, you get something known as a direct product structure, right? So the total Hilbert space of the system is a product of the Hilbert spaces of this and that. And any state, so it's made up of states of the form phi belonging to HA and psi belonging to HA, phi belonging to HB. And you can, of course, add any arbitrary number of such states. And those which can be written as in this form, they are known as separable states. We'll only look at sort of the pure state formulation. So if you have the proper description of it comes in the language of density matrices, but we'll only look at state vector formulation here, right? So these are known as separable states. Entangled states are those which can't be separated in this way. There's a lot of them in the Hilbert space. Okay, so that's good. So now, yeah, if you look at the computational basis, these are separable states. And an arbitrary state can be written in this way. And these are the entangled states which form a basis. These are known as EPR or Bell states. Sorry? Entanglement is a purely quantum phenomenon. Yeah, there's no classical counterpart to those. That's been done in many experiments that violation of Bell's inequality have been found in. So, okay, yeah, good. The next slide is that. So now, what was wrong with, okay, so was I audible before? Okay. So, in that first slide, right, we saw how ChatGPT was summarizing this. It used the word instantaneously affect the measurement of the other qubit, in the state of the other qubit. So this type of language you should not be using. So the language can be very confusing. For example, they talk about locality, realism, and all of that. My approach and sort of this is the view one should have. One is, when one is a practitioner in the field, you just look at those operators and try to work with the postulates. There is no reason to think of all of these philosophical issues, or locality, realism, things like that. 70, 80 years ago, that is fine, but now things have been settled, right? It's not spooky. Entanglement is not spooky. For example, John Bell, he talks about this experiment in one of his papers, thought experiment, where there's this professor, Bertelmann, and he wears socks which one of them is always pink and the other is green, some other color. He used to dress like that. Apparently it's a real person. And this is an image taken from the Wikipedia page. You can look at that, search for that Bertelmann socks. So now, this is classically correlated information. That is, if I see one of his socks to be pink, I know immediately that the other has to be green or not pink. Now, if I were to wrap one of the socks, both the socks in different boxes, send one to Mars, and open the box that I have, I immediately can conclude what is there is no affront to special theory of relativity, causality, any of these things. Okay, so in the same way, you are supposed to understand that measurement of one of them, it's not an affront to what the other person is measuring. It's not a, so, but the thing is that correlations in the quantum realm, it can be something more. That is, you can measure one property of the other and get the corresponding property of, one property of Alice's qubit and get the corresponding property of Bob's. And you can choose which property. You can do measurements along X and Z. So those are the correlations that are purely quantum, that don't exist in the classical world. So I urge you to go read this CHSH experiment. It's a small section in Nielsen and Chuang. Just work out those details for yourself. There are 2 measurements that Alice can make and 2 measurements that Bob can make. And work it out in the quantum setting, which is, these are just operators and you have to find the expectation values. Okay, just use the postulate, the measurement postulate, right? Work it out. And if it were to behave like classical random variables, you can see what that would work out to. And you'll see that the inequality that you get in the classical setting will be violated in the quantum case. And that's about it. You can get into all of these issues about realism and locality, but really you should, that's something that is spooky 70, 80 years ago. It's not anymore. And it was for good reason back then, because they were still learning things about quantum mechanics. Now there's a long time that has passed, and this year they have been given the Nobel for the experiments done by alien aspect, right? So now let me switch gears. So one more property that quantum information has is that you can't just copy a quantum state. This is called the no cloning theorem. So show of hands, who is familiar with this? Okay, fair chunk. So so why is it, there's a very simple reason why this is a property of quantum information. It's because there is no linear operator that can take me from this state, if I start with this state, into that state. And that's it. Sorry? Yeah, not only unitary, but there's no linear transformation also. There's no linear transformation that you can make on that. You can do it for specific states like 0, 0, you can set up things like that. But okay, so, but you can actually teleport quantum information in the sense you can use an entangled qubit, that is a system of 2 qubits which are entangled. Give one to Alice and give one to Bob, and based on the measurements that Alice makes, Bob can fix up his qubit to retrieve that state. Okay, so you should work these things out for yourself. Okay, so now I think we are switching gears, going into quantum machine learning. So there's a popular view that supervised quantum machine learning is a kernel method. Again, whenever we talk of quantum machine learning, we are usually working in this type of hybrid setting, where the optimization problem is solved on a classical machine and kernel evaluations are done on the quantum machine. So let me stop here. Were there any questions for the previous portion? No? Great. Okay. So now, so what is a support vector machine? Suppose in the supervised learning paradigm, right, you are given some training data, and say each is labeled plus or minus 1, and suppose your task is you have to draw a line between these 2 classes. You have to draw it in such a way that the classes will separate out, and if I go and if I ask you to take this classifier to the field and test it on an unseen data set, it should do well there. So that is known as the generalizability. And this is one of the earliest, ways of looking at machine learning before all of the deep neural networks and things like that. Well, GPUs really allowed that kind of neural networks to be very successful. But what is nice is that these have performance guarantees, such as support vector machines. These have performance guarantees. So you can mathematically show that you can bound the generalization error on an unseen test set and things like that. So for that reason, it's a very, very crucial method with very strong mathematical guarantees on that. And so what does it do? What kind of line should I draw here? So I can draw many lines which can separate out the classes, right? Hyperplane, right? I'll draw a linear boundary. Let's say they are linearly separable. What kind of line should I draw? I'll draw something that exactly. So exactly. Maximum margin. I'll try to maximize this margin. And I'll draw my boundary in the middle of that. Okay? So that you can pose as an optimization problem. It's a convex optimization problem which you solve. And do you know what kernel methods are? Good. Right. Right. Yeah. So what you do is you embed the data that is given to you into a much higher dimensional space and then draw a linear boundary in that space. So that space is known as the feature space, the higher dimensional space. Take this example. There is no way that you can draw like a line which will separate out the red and blue points, right? So what it is a circle. So what can I do? I can project it onto like a parabola in 3 dimensions, right? And all of these red points are at the bottom of this. And then I can draw like a hyperplane which separates that out. So using this kind of method, you can draw really nonlinear boundaries in the original data space. And what is crucial in this, using this kernel trick, is that you don't actually have to evaluate those vectors in the feature space. You only need to efficiently evaluate inner products. That's a very important thing. So that inner product is called the kernel. That's the kernel function. So now what are quantum kernels? So you have a state which is starting in the computational basis, and you can, say you have some data, and at the end of it you get some quantum state which depends on the data that you have. X is the data, okay? And this embeds the classical data into a quantum state, and what it is, it's a unitary transformation on this computational basis. And you can think of the density matrix as the vector in the feature Hilbert space. That's how we'll define the kernel. So what is the density matrix if I have this? It's the outer product, right? It's the outer product phi, and right? So and so my task is to evaluate inner products like this efficiently. And this can be done very efficiently in quantum computers. Using quantum computers, this is very efficient to compute. So you see an immediate parallel with the kernel, with the classical kernel trick, that you don't actually need explicitly to know what these phi of x and phi of x prime are. I just need to know how to evaluate this inner product. Or I don't have to know the density matrices themselves. I don't have to perform like quantum state tomography or something like that. I can write up a circuit which evaluates this inner product, a quantum circuit. In fact, you can write it with just 2 unitary gates if you use this 2 two unitary operations, one to create this and one to create that. Is there anybody familiar with the swap circuit? It's quite a popular one. Okay, good. So what kind of kernels can be realized in the quantum setting? I'd urge you to go look at this paper. It's a 2021 archive. So these are all of the kind of kernels. So you can also get the Gaussian kernel. This is very widely used in classical kernel methods. Okay, so I'm keeping this portion extremely short. How am I doing on the time? Okay. So, all right. So, what is the big deal about quantum kernels? They can offer sort of speedups in the sense that some kernels are hard to simulate classically, right? So, maybe for some data sets you will find speedups and all that. So, this paper, it gave a kernel which is evaluated by this circuit, or embeddings which are evaluated by this circuit. And the inner products of these encodings are known to be sharp P hard. This is a complexity class. I mean, I don't know the details of this complexity class, but like classically, it is a hard thing to get. And one more thing is discrete log is also classically hard, right? That is known. So we can have a quantum kernel to represent it efficiently, but not classical kernels. So using that particular example, this paper was able to show a rigorous and robust speed up in the supervised quantum setting. So, okay, so there is some purpose in sort of exploring along this direction. So now we'll go back to how these kernels are evaluated. So I have to evaluate this inner product. I can use one of these two circuits. This is the swap circuit. So this is there, all of it is in Nielsen and Chuanga. Again, this type of swap circuit is used in many different applications. And very importantly, the kernel function has to be estimated from the measurement statistics of these circuits. Right? You don't directly get to evaluate this. So in quantum computing, you have to do measurements again and again. So that sort of introduces a new problem that was not there in the classical setting. So depending on the amount of precision you want in the kernel, you will have to evaluate more number of times, right? Yeah, because for example, look at this. How do I infer the kernel? In this circuit, I measure the ancillary bit, this ancillary Q bit. If I get a 0, then the kernel value is 0. If I get a 1, then the kernel value is 1. Now, I have to do it like 1,000 times. Maybe it gives me 750 times 0, some 250 times 1. So what is the kernel value that I infer? It's the expected value, right? 0.25 I get. But what if I just do one measurement? I'll either get 0 or 1. So a huge error, right? Like maybe the true value is not even this. If I run it another 1,000 times, I'll totally get a different output there. So this is a huge problem. And sort of this is a problem that has not been studied carefully in the quantum machine learning literature. So we sort of, you can look at this table, for example, the number of measurements they are using, what I just said. 50,000 here, 2,000 in this, 3,000. There is no real sort of systematic approach to how much you need, so on and so forth. And IBM Q defaults were 1024 in 2021, and now they give you 4,000 measurement shots. It's actually a variable you can set. when you use Qiskit or any of those at the back end. So, has anyone, how many have run actual back-end quantum computations here? Oh, very nice. Okay, so so this paper, for example, right? Look at this. It's reporting the accuracies. There's a huge range on which it can vary. If you do the experiment again and again, you get like a huge variation in that. And they're plotting the average accuracy here, which is also not very high. And here they're doing it as a function of number of measurements. So you can run this type of experiment on your computer to see how much, what kind of discrepancies you get in the accuracy of a data set. So you can see like somewhere around here, my accuracies can be from 0.5 all the way to 0.9, right? Like if I look at n here, it's a huge range. So like on Monday, if I get like 0.5 accuracy, on Tuesday I can get 90% accuracy. So 50% accuracy is meaningless. It's just a random assignment of labels, right? And 90% is quite good. So one has to sort of come up with a metric which captures the reliability of this classifier. So it's not very reliable. Once I run it, it's so low. Another time I run it, it's very high. And you can't just look at the average accuracy. You want this classification label to give the same label every time you run this. Every time you run the classifier using, say, n measurement shots. If I use the same n measurement shots on a different day, I can't be coming up with a different label. That's no good. So you need reliable classification. So, so the question is, how many measurements should we use to reproduce reliably the labels of the classifier? So it's not enough to just give a label. You have to be able to reliably reproduce that. So this has been done over 200 independent trials, so you're seeing a huge spread. So you need to first come up with a better error metric to capture that. So okay, so how many measurements you need is very important question. If it scales very poorly with some parameters of the problem, then all this talk about quantum advantages and all that, it goes out of the window. There's no meaning to that. So if you want to precisely evaluate for a data set of size m all of the kernel entries, then you need m squared by epsilon squared number of measurements. Epsilon is the precision in operator distance here. Right? So how many are familiar with the Chernoff bounds or any of the concentration bounds? Okay, so you can derive these. Are people familiar with this omega notation? Asymptotic lower bound? Okay. So now there's a NeurIPS paper that was published in 2021 which said if exponential precision is needed for your task, whatever task you have. So in evaluating the kernels, if you need exponential precision, then all your advantages disappear. Because epsilon goes to 0, n I need is infinite. There's no hope. There's no hope of using this quantum computer to even get an advantage. Doesn't matter what platform you're on. So, because quantum measurements are a fundamental thing. You have to do it on all platforms. So now we ask these three questions. Is there a better metric to measure the reliability? Can we obtain a better scaling? This is looking polynomial in that and 1 over epsilon squared. Can we reduce n without, can you reduce n even further without sacrificing the reliability of the classifier. So these are the questions we attempt. This reliability you can define as the probability with which your stochastic classifier, that is the classifier that I get by using n measurements per kernel entry, the probability with which it agrees with the ideal quantum kernel classifier. The ideal case is when n is going to infinity, right? If you have infinite measurements, then you can very accurately say what is the expected value of that variable. So, so we show reliable classification requires log m by gamma squared. So that is an exponential improvement on m on the data set size. And gamma is not vanishingly small. This is very important. Gamma is analogous to the precision. Well, precision, if you want a very precise thing, then epsilon goes to 0. But gamma, if you choose a nice kernel function, then you can have gamma of order 1. So this is a very, very good improvement. Can we reduce it even further? You can use techniques from chance constraint programming to do that. So it's a type of technique that deals with stochasticity in an optimization problem. You know, like the SVM optimization problem has an objective which is stochastic, because the kernel itself is stochastic here. So you can sort of use techniques from chance constraint optimization and get a nice reduction in the number of measurements. So just to give you some intuition, you can derive this type of theorem. This G star of x here is actually the classifier function. Well, the sign of this will tell you the label of the class. So if I want to assign a label to the class x, I'll say, what is the sign of G star of x? Okay? And this is for the ideal case. Stars represent the ideal cases where n goes to infinity. And what is the probability that if n of x agrees with this classifier? You can derive a Chernoff bound for that, where C is the circuit factor, which depends on whether you're using the gate circuit or the swap circuit. It actually leads to different measurement statistics. What this tells us is, this depends inversely on G star of x. So if you are closer to the margin of that, or the decision boundary, if you're closer to the decision boundary, then you'll need more number of measurements. That is, you need more precise kernel evaluations, because noise can put you over to the other side. So you can generalize this result to a data set of size m, arbitrary data set. So this is sort of, these circles represent the amount of, the area of the circle represents how many shots are needed. Okay, so this chance constraint optimization, I don't think we'll have time to cover that at all. But I want to say what kind of savings that it can show over the naive SVM. So first of all, we derived better bounds, and we are using those bounds to compare. So you can do this chance constraint programming and get like upwards of 90% savings in the number of measurements needed in many cases. And importantly, like, for example, these numbers are not listed in most of the studies that happen. It seems the community is not that interested in looking at the reliability. It's just happy with very large ranges of accuracy and just reporting average accuracies. So we can have a direct comparison, because these guys actually list the number of shots. They need 50,000. We need 32 to do the same. Okay, that's my time. I just want to give you an overview of what other things are happening in quantum machine learning literature. Very interesting things. Okay, this work was done in collaboration with Apurva and Chiranjeev and Apurva's student who is now at Los Alamos. And there's this quantum recommendation systems problem. So it made a lot of news in this quantum machine learning literature. So the idea is to find a classical, they say this is an open problem, find a classical recommendation algorithm. In this particular paper, they're stating this, which requires a time, a polynomial in K. We'll come to what, like K is the low rank representation of a preference matrix, and M and N are the dimensions of that matrix. You can go into the details of this problem, but the point is, these guys had derived a quantum algorithm for this problem, which is exponentially faster than the best known classical algorithm at the time. So it made a lot of news. But later, Evan Tang, who was just an undergrad, she was 19 years old, she was advised by Scott Aronson, and she showed that you can do this classically as well, if you are given a certain type of input access. This calls it the sampling and query access to the data. If you are given that type of access, then you can do it classically as well. So this type of thing was, they call it dequantizing. She calls it dequantizing the algorithm. So, or quantum inspired classical algorithms. So very interesting work. And she's managed to dequantize many papers so far. You can see quantum principal component analysis. So many recent papers. These are citation numbers that you can see and the years. Just taken it from Google Scholar, right? So there's a lot of work to be, okay, this ends my talk. All right, thank you for listening.
Sir, quantum machine learning, I mean, how quantum machine learning is contributing to machine learning? For example, machine learning has some set of problems, like explainable AI or time. Like, how exactly it is contributing?
At this moment, it's not very clear what the exact contributions are from the quantum side. There's a lot to be explored. Like, for example, supervised quantum machine learning has been explored to some extent. For example, the kernel methods and all that. But unsupervised settings are not really explored. So there's a lot of room to see what exactly the implications of quantum computing are to this machine learning literature.
Sir, I have heard something called as quantum data.
Quantum?
Data. Quantum data.
Yeah, that's where you can have most. If you have quantum data, it's definitely better to do learning on a quantum, in a fully quantum setting.
Okay.
Because you don't lose the coherences and other kinds of quantum correlations that you have. So,
how can you prepare such data?
Sorry?
How can you prepare such data?
It can come out from experiments, like there needs to be some way to sort of take in the quantum state of some experimental system and then sort of process it on a quantum computer.
Okay.
So maybe we can chat more about this.
Yeah, okay.
I think Apurva.
Hello, sir.
Yeah.
So, I have a general question. So, you had mentioned how ChatGPT's definition or Michio Kaku's definition is not precise. And so, how can we explain quantum mechanics or quantum technology to a layman or any middle schooler without using these kind of definitions?
There is no reason to explain. They have to go and work out the things themselves.
Okay.
That's why.
Okay. Yeah. Okay. Yeah.
Because just adds to confusion. There's no, because words can be very imprecise. You go and write the equations and
Okay, because, we have to somehow kindle the interest among the younger generation. So without introducing linear algebra or operators and everything, so how can we just, introduce it?
I think I don't really know how to answer that, because people grow up with classical intuition whether you like it or not.
Okay.
Because there is no other way to understand the world, right? When you're...
Okay. Yeah. Okay.
Yeah, that's right. You can save it for a
question. My question was that in first you discussed about that classical how SVM works. So if we have 2 dimensions, we increase one more dimension or more than one, and we use the hyperplane for that. But in quantum kernel, you said that we work with each data points, iterate more than n number of time, consider 1024 of time.
Yeah.
And then we calculate probability of each and every data points, and then we classify that thing. So don't you think...
No. You're evaluating the kernel. This is the same procedure. The kernel is again like it's a different high dimensional feature space and all of that. You are measuring it many times in order to say what that value of the kernel is, because you don't directly have access to that kernel. You have to, it's inside that, it's the inner product of these 2 states, or the transition amplitude, transition probability between 2 quantum states. You don't directly get access to that. You have to do measurements.
Means after measuring, we get each data point classification.
You have to do it for each pair of data points.
Each pair of data
points.
Then after, don't you think that whatever the probability data we get, it will be so much accurate, means so much non-linear classification that it can cause overfitting?
No. That is decided by the kernel choice. What kind of boundary you can get, whether it can linearly separate in that feature space. That is kernel choice. That has nothing to do with what you're doing on the quantum machine. You can have any kernel choice and like give a circuit, a quantum circuit which can do evaluations of that kernel. It's just to pinpoint what that value is, I have to measure it many times.
And you said we can't, one more last question just, that you said in starting only, that we can't say that the quantum computer can process in superposition more than one state parallelly.
More than?
Means in superposition you said that so many of them think that quantum computer process multiple possibilities if you have 4 qubits.
Yeah, that is a very bad way of...
Means how then we can define, means does it it can have more than one state, or it doesn't have more than one state every time?
It has a state.
But we can't define
if you want to do measurements in a certain basis, then you have to, conduct those measurements and get it out. That is what superposition is, right? It's just a state. It just happens to, you can expand it out in any basis. That is. Yeah. It's any vector in Hilbert space. That's all there is to it.
It's not all vector, any.
Yeah, any vector.
Sir, on what basis we decide our quantum kernel?
On what basis? That's again a practitioner's art. One of the main questions is to not only quantum kernel, any kernel. That's a practitioner's art. There is no clear way to, if people were to give, okay, for this data set, use this kernel, then there's no need for neural networks. It's far more efficient. There's no need for any of the deep learning, whatever. But the thing is, it's very hard to know what kernel to use to separate out that data set. It's very data set dependent. It's a practitioner's art.
Okay.
Yeah. Thank you.